But sir, the numbers have reduced significantly, sir.
Oh, really?
I think so. From the first day,
Mm-hmm.
I don't know.
So we are live on YouTube. We can start now.
Okay, very good afternoon to all who have joined online. The topic of my talk today is phase transitions under high pressures. So basically, I have split my next two talks in two parts. In first part, I will talk about the phase transitions in general, not specific to high pressures. And then in the second talk, I will be more specific to the high pressure phase transitions. And before I begin, I would like to comment about the last talk I gave on equation of state. So you might have noticed that in all the equation of state, though in the first I introduced equation of state as a function of pressure, volume, and temperature as equal to 0. That implies a surface on the PVT three-dimensional plot. And I mainly focused on the isotherms. So in that case, T is constant. So when you take the projection of this equation of state surface on the temperature axis, taking T is equal to some constant, the line basically, which depends on pressure and volume only. But of course, I would like to comment that the temperature part is inbuilt in the equation of states. So even in static compressions also, when you raise the pressure, there should be some increase in temperature, but slowly as the system relaxes, the temperature is taken away by the system, by the thermoconductivity of the sample environment. But in case of dynamic compression experiments, of course, there will be significant rise in the temperatures. So then the part contributing to temperature, contributing to pressure will become significant, and Wilson parameter and other things will be important to consider. So, okay, now let me begin with the talk today. So as I told, I will be focusing this talk primarily on the general aspects of phase transitions. So I will first start with a general introduction to phase transitions and phase diagrams, and subsequently I will give a brief description of different classifications of phase transitions based on thermodynamics, the mechanism of phase transition, kinetic of phase transition, and the symmetry. And then I will also discuss about the phenomenological theories of phase transitions. Of course, a deeper understanding will come from the microscopic picture of the phase transition, where you monitor these atomic movements. But I will be concentrating on phenomenological theories, which by and large describes these phase transitions. So before we define phase transition, we should know what is a phase. So as we discussed in last talk, that a thermodynamic state of the system which follows a unique equation of state can be stated as a phase. So a phase should have uniform physical properties, and it should be described by some unique internal configuration. By here, I will be mostly concerned about the structural phase transition. So by internal configuration, I mean the structure of the phase. So depending on the internal structure of the system, there will be a phase or configuration which will have some uniform physical properties. And so this definition by itself implies that we can define the phase transition also. So whenever there is a spontaneous change in the internal configuration, then there is a change in the equation of state, and this describes the phase transition. Here I would like to emphasize the word spontaneous. So spontaneous means without any influence of external field, the property of system changes. For example, if you consider a paramagnetic phase and if you apply magnetic field, you can induce magnetization in the system. But this is not a phase transition. A phase transition, which is also called this para to ferro phase transition, ferromagnetic phase transition, where you have a spontaneous magnetization in the system, even in zero magnetic. So this is the phase transition, and this cartoon depicts typical phase transition For example, this gas liquid phase transition in water. So this is the pressure volume curve, and you can see in this pressure volume curve, I have plotted different red curves, which are basically isotherms. So you process the system in different pressure volume regions, so at some constant temperature. And if you are at temperature T1 and T2 below Tc, what you see there, that there is a discontinuity in volume. So this signifies the phase transition. So in this case, of course, there is a blue region that I have marked here. This corresponds to the spinodal region. We will discuss about it in a moment later. But these isotherms clearly shows that there is a phase transition. So there is one isotherm which corresponds to some critical temperature Tc, where we have a point of inflection, which actually corresponds to the tip of this spinodal region. That is basically the critical point where the nature of phase transition changes, but still it signifies the phase transition. And above, very much above this Tc, you can see this kind of curve where there is a continuous change. So we cannot distinguish between the liquid and vapor phase in this case. So phase transitions are not only induced by the change in the thermodynamic conditions, it can also be induced by the chemical compositional change. And this basically gives us a phase diagram. It can be thermodynamic parameter dependent, or it can be compositional dependent. For example, here I have shown 3 phase diagrams, where this is the typical phase diagram of water or H2O in different phases as a function of pressure and temperature only. So this corresponds to the solid phase, and this phase corresponds to the liquid phase, and this region corresponds to the vapor phase. These lines that you see here, they correspond to the phase coexistence. This is a triple point where all these 3 phases are in equilibrium. And this is a special point called critical point, where the nature of phase transition changes. And another kind of phase transition generally metallurgists deal with, where they actually change the composition. For example, this is a typical phase diagram of alloying A and B chemicals or elements. And you see this kind of phase transition where you have some phase at very low concentration of B, and another phase at very high concentration of B, and then you have a liquid phase, and then you have a point, dip point, which corresponds to the epictoid, which has the lowest melting temperature. So we will not be dealing with this kind of phase transition in this talk, because we will be mostly concerned with a thermodynamical change in the system to induce the phase transitions. This is one more example I have shown here of the morphotropic phase boundary. This is again a phase change because of the composition in the solid solution. For example, in this lead zirconium titanate, we have solid solution of PbZrO3 and PbTiO3. And as you increase the concentration, mole fraction of the PbTiO3, you can go across this phase boundary where your rhomohedral structure changes to this tetragonal structure. So this is very much of interest from applied point of view, because here you get very large dielectric constant, and people have been doing this research on various piezoelectric materials, ferroelectric materials, in order to have this morphotropic phase boundary. In fact, there are studies where it has been shown that even in pure systems, you can go across this morphotropic phase boundaries by application of pressure on. Okay, so we will be mainly focusing on the phase transitions, where we change the thermodynamic parameter in order to introduce the phase transitions. So this is another elaborate picture of the same phase diagram of water. So earlier I had shown only this region where you have solid, liquid and vapor phase. But in fact, this is one of the interesting problems in high pressure physics, to study different phases of water at different pressure and temperature conditions in order to understand the phases of water at different in astrophysics at different thermodynamic conditions, at different planets, at different planetary interiors. So various phases people have found out under the pressure and temperature studies. So basically, this is the main motivation of studying these phase transitions under high pressure, temperature, and thermodynamic parameters in order to establish these phase diagrams and to know what will be the stable phase under given thermodynamic conditions. Another interesting part is also to study how this phase changes as you cross the phase boundary. So what is the mechanism of this phase transition? This is also interesting from basic physics point of view. So this is also the reason why people study the phase transitions under high pressure temperature. Okay, now let me come to the second part of my talk. So now I will talk about the classifications of phase transitions. So the very first attempt to classify the phase transition, of course, I will talk first about thermodynamic classification of phase transition. The first attempt was made by Ernst in early 1930s. And he basically classified the phase transition in terms of the discontinuities in the first order derivative of free energy. So thermodynamically, we know that system always tries to go in a phase or in a state where the free energy is minimized. So how it goes from one state to another state. So this will correspond to some change in the derivatives of free energy. So if the first order derivative is discontinuous, you call it a first order phase transition. For example, first order derivatives corresponds to change in density or change in entropy. So if you have discontinuity in these quantities, you can call it a first order phase transition. And if you have discontinuity in the second order derivative of free energy, then you call it a second order phase transition. For example, specific heat, susceptibility, these are the second order derivative of free energies. So if you have discontinuities in these quantities, this will be called a second order phase transition. And of course, the same thing can be extended to higher order phase transition, but we will not talk about this because this corresponds to basically the derivative of physical quantity described by the second order phase transition. So now this classification actually could not explain some of the things like the behavior at the critical point. At the critical point, we know that all the derivatives become zero. So we cannot define the order of phase transition there. Also, the specific heat of in magnetic transition. So as per this classification, the specific heat across the magnetic phase transition should have a discontinuity. Whereas it has been shown that it is not a discontinuity, you have a lambda point, you have a divergence of specific heat across this magnetic transition. So researchers have actually come over this classification, and now there is a new approach to define thermodynamically different classes of phase transitions. So typically now they call it a first order phase transition or discontinuous phase transition, which involves a latent heat. And during such transition, a system either absorbs or releases a fixed amount of energy per volume. So this is the famous Clapeyron relationship, where you see the change in pressure as a function of temperature given by this latent heat divided by the volume change across the phase transition. Of course, this can be positive or negative depending on from which direction you go. For example, if you go from water phase to a vapor phase, you would need some energy. If you go from a gaseous phase to liquid phase, some energy will be. So this can be written as change in entropy versus change in volume, and there is some finite value of this. So this corresponds to the first order phase transitions. And if you look at the free energies, what you will see that at first order phase transitions, there will be a change, clear-cut change in the free energy curve. For example, this curve corresponds to the free energy of one phase, and this curve corresponds to the free energy of other phase. And as soon as there is a phase transition, the system switch over from one phase to other phase. Whereas there are continuous phase transitions, and which are signified basically which are characterized by divergent susceptibilities, infinite correlation lengths, and power law decay of correlations near criticality. These kind of continuous phase transitions are second kind of phase transitions. And the very example that I gave for water, actually this describes both kind of phase transitions at T below Tc and at Tc. So this is the modern classification of phase transitions as a function of thermodynamic parameters. Another way to classify the phase transition is based on the mechanism, how phase transitions takes place. So here I will basically focus on phase transition in solids. So one method, this was given by Berger long back in 1960s, and he basically gave that there can be two kind of phase transitions, reconstructive and displacing. So a reconstructive phase transition involves a major reorganization of crystal structure in which many bonds have to be broken and new bonds have to be formed. For example, graphite to diamond transition, or quartz to crystallobrite transition in SiO2. These are the examples of the reconstructive phase transitions. Whereas there could be phase transitions which involve very little movement of atoms, involve the distortion of bonds rather than breaking, and the structure changes that occur usually very small. For example, in this cartoon, you can see if you have a structure like A and this is to be transformed to B, C, or D, many bonds have to be broken and some new bonds have to be formed. So any transition from A to any B, C, D will be reconstructive kind. Whereas if you compare these three structures, B, C, and D, so very small change in atomic positions will lead to this transition. This is an example of displacive kind of phase transitions. So energetically, if you see, because here you have to break several bonds, form new bonds, there should be a large barrier in the configurational space of free energy. So this is a cartoon to just show how free energy should change in the configurational space across the phase transition. So this may be the initial phase, this may be the final phase, which has become now stable. This is a metastable, but in order to go from here to here, one has to cross this barrier. So this reconstructive phase transitions should show some kinetic effects with time, and it should depend on the barrier and depending on the temperature, the accessibility of this phase. I will talk about kinetics later, but we can understand this reconstructive by this cartoon of free energy. At the same time, here I have shown very small displacement of atoms can lead to the displacive phase transitions. So this can be understood as a very small or negligible barrier between two phases. Actually, this can be even barrierless when we apply field. So actually, this kind of phase transitions are this mechanism is basically responsible for most of the phase transitions that we study under high pressures, because high pressures should reduce the diffusion. And in this case, in reconstructive, you need diffusion. And so the phase transition should be taking place through a path which requires minimal atomic displacement. So this could be the probable candidate to explain the phase transitions under high pressures. Okay, now coming to the classification of phase transition based on kinetics. So you can classify this based on kinetics in three types of phase transitions: very slow, which are quenchable, for example, diamond to graphite phase transition, and in CDS using sulfide to NaCl kind of structure, this kind of phase transitions, these are very slow. Or there can be intermediate kinetic. For example, in this AuCu3, this order disorder phase transition, this is intermediate. And there can be a very rapid phase transitions. For example, FCC to BCT transition in thorium, omega to beta transition in zirconium. Actually, these classifications are quite relative and subjective because one can tune the quenchability or the kinetic of this phase transition by temperature as well as the external field like pressure. For example, here I have shown you the transition in KCl to the B2 phase. So B2 phase is cesium chloride kind of phase. And you can see as you increase pressure, and the concentration of this B2 phase increases very rapidly. So this shows very fast kinetics at high pressure. So you can change the kinetics by applying pressure. And at the same time, there could be other studies also where people have shown that with temperature also, you can tune the kinetics of the phase transition. For example, here at lower temperatures, at 330 degrees centigrade, you have this curve for the kinetics. At very high temperatures like 530, you have this kind of kinetics. This in case of GO2 at certain constant pressures. So this is consistent with the free energy curve that we have seen in the previous slide. So what happens, this external field like pressure, this modifies the energy barrier. So at constant temperature, you can increase the kinetics by changing the external field. And then because this kinetic barrier has some height and there is some finite probability at particular temperature to cross this barrier, so you can also enhance the kinetics by increasing temperature. Okay, another important classification is based on symmetry. Actually, this is something that is more relevant for high pressure phase transitions, where I told that very little displacements of the atoms give rise to the phase transitions. So when there is a little movement of atoms, there can be some, we can associate some symmetry to the parent and daughter phase. So we can classify phase transition based on symmetry, like in these four groups, like isosymmetric phase transition, where parent and daughter phase have same symmetry. So this kind of phase transitions occur generally when there is an electronic phase transition. Then there can be group subgroup symmetry relationship, where the daughter phase is low symmetry phase, but it is subgroup of the parent phase. Then there could be a phase transitions where it is intersection group. So parent and daughter phase both are related to the intermediate phase by some group subgroup relationship. And then there could be order disorder kind of phase transition also. For example, if there are some steric hindrances and system is not able to go to some configuration which is thermodynamically more stable, and because of kinetic constraints, it basically is stuck to some disorder phase, like amorphization can happen. So this kind of transitions can be called as order disorder phase transitions. So this classification has been nicely reviewed in this article by Dr. Gupta and Chidambar. So I will discuss more detail about this kind of phase transitions when I will concentrate on pressure-induced phase transition in my next lecture. Okay, so to summarize, we can plot these different classifications on a three-dimensional plot based on thermodynamics, based on kinetics, or based on structure, based on the mechanism, based on symmetry. So these actually are interrelated in some sense. Like I told, transitions which involve very large amount of reconstruction, that will have that will require some finite amount of change in enthalpies, change in volume, and because there is a large energy requirement, so it should be slow also. So this can be related to thermodynamically to first order phase transitions, and then there could be very rapid reversible changes, which can be related also to first order phase transitions, but with very small change in the internal energy. And anyway, I have already discussed this reconstructive, displacive, and different symmetry type of phase transitions. So these are all interrelated. Here I have shown some example of these different type of phase transition as classified based on the kinetics, classified based on the thermodynamics, and also classified based on the mechanism of phase transition. For example, this diamond to graphite or graphite diamond transition. So this is a reconstructive kind of phase transition which require large amount of volume change, some finite Alp change, first order phase transition. And because this requires large energy, this costs large energy, it is also very slow. So this can be quenchable. In fact, that is the reason why we are able to have diamond under ambient conditions. Diamond is a metastable phase, but still we use it under ambient conditions. In fact, whole high pressure physics research is based on the diamond phase of carbon. And then these are the examples of intermediate kinetics, which can have mixed order, could be second order, it could be first order, and then very rapid phase transitions, and this could be first order phase transitions, which may have basically coordinated movement of atoms leading to the phase transitions. And these are also called Martinsitic phase transitions. I will discuss this in detail in my second part of the talk. Okay, now I come to the third part of my talk today. That is the phenomenological theories of phase transition. I call it a phenomenological theory because these basically describe the phase transition in general, and the basic mechanism of this phase transition, basic theories of these phase transitions. And one can actually explain all different kind of phase transitions by these phenomenological theories. Some inputs, some parameters can be inserted in these theories to have the quantitative description of the phase transitions. So first I will talk about the classical nucleation and growth process. So this is generally the mechanism of reconstructive phase transitions. In this process, we explain the transition taking place through large thermal fluctuations. So because of the thermal fluctuations, there will be nucleation. As soon as your thermodynamic state is in the region which can stabilize the daughter phase or product phase, so there are always fluctuations in the system. So there will be always nucleations also in the system, but not all the nuclei that will be formed due to thermal fluctuation will grow. So there will be some critical radius of the nucleus above which it will grow, and those nuclei which are randomly formed because of thermal fluctuation, but which have lower radii than the critical radii, they will perish. And as soon as you have some suitable nuclei, then it will grow. And as soon as it grows, there are interface formations, and then there will be ripening. So it will be growth of large domain at the expense of smaller domains. So the example of this kind of phase transitions could be liquid to solid phase transitions. It could be crystallization, could be gas-liquid transition, and it can be orientational disorder order transition, for example, in liquid crystals. So one of the assumptions of this nucleation and growth process is that the formation of the nuclei is spherical. And the second phase, which is the stable phase now in new thermodynamic condition, is arising in the background of this metastable phase. Okay, and we can actually quantify the formation of this critical nuclei by the free energy change. So if we consider the free energy change because of the formation of this nuclei, it can have two parts. One is the surface part and other is the volume part. So of course, because the second phase is now stable phase and first phase is the metastable phase. So any region which is transformed to the second phase will reduce the free energy. So this volume part should have a negative contribution. But the interface between this phase 1 and phase 2 will have a positive contribution to the free energy, because this will have some structure which will be relatively more disordered in comparison to the first and second phase. So the surface part will have a positive contribution. And the sum of these two parts leads to this kind of curve, which has some critical radii, which corresponds to the maximum delta G. Now, why I call it a critical radii? Because if there is a nuclei which is formed with radii lower than this, for this, in order to grow, the free energy has to increase. So, which is thermodynamically not supported. So, all the nuclei which are formed with radii below R star, they will actually perish. Whereas there will be nuclei which will have radius higher than this critical radii, they will fall in this region. And as it grows, the Gibbs energy decreases. So the thermodynamics supports the growth of this kind of nuclei. So we can calculate the critical nuclei from this expression by taking the derivative of this expression, find out the critical radii at which the derivative is 0. And then we can calculate, we can estimate what will be the cost, and this will depend on the change in free energy of the parent and daughter phase. So besides this nucleation, another thing important is the nucleation rate. So as I told, at given at given temperature, you have to have some fluctuations which can give rise to this kind of nucleation. Because the formation of this critical nuclei requires some energy. So there will be a Boltzmann factor, which basically describes the probability of formation of such nuclei. So we can define nucleation rate like this, which is multiplied by some constant, and this of course depends on the model, on some specific system which we are studying. And then there is a growth process. By growth process, I mean these nuclei have to actually grow. So the interface has to grow. Some atoms which are part of phase 1 has to become a part of phase 2. So there will be some activation energy required. Besides this formation of this nuclei, you also require some activation energy in order to grow this nuclei. So this is expressed by these terms. And this way we can describe the phase transition in the classical nucleation and growth process. Of course, in this theory, we have considered homogeneous nucleation. By homogeneous nucleation, I mean the probability of nucleation is same at different locations. So there may be cases where there is a heterogeneous nucleation. For example, Martinsitic phase transitions. They cannot be explained by homogeneous nucleation. For that, one has to invoke heterogeneous nucleation theory. So in that case, there will be some sites where the probability of nucleation is more. So there will be some defect sites, maybe some stress concentrators. So we will discuss about these things when I will talk about the plastic strain-induced phase transitions. Okay. So generally, this reconstructive phase transition mechanism or this nucleation and growth process is not used to explain phase transitions under high pressures. But as I mentioned, in case of crystallization, especially where you have a negative Clapeyron slope, so by negative Clapeyron slope, I mean the liquid phase has higher density than the solid phase. So as you increase pressure, the melting point comes down. So you can reach a pressure where there can be a significant enhancement in the diffusion, and you can invoke this nucleation and growth process. In fact, we have used this nucleation and growth process in order to explain the preferred crystallization in amorphous silicon. So we know that crystalline silicon has a cubic diamond phase under ambient conditions. As you increase pressure, it goes to a beta tin phase, tetragonal phase, and then it goes to some IMMA phase, and then there is a phase called primitive hexagonal phase. But when we pressurize the amorphous silicon, which has coordination more or less very close to the cubic diamond phase, that is 4, we were expecting crystallization or maybe a transition to a phase which have coordination equivalent to the beta tin phase, which is 6 coordinate. But we found that under pressure, there is no crystallization to beta tin phase, but it directly crystallizes to the primitive hexagonal phase. So now we wanted to explain why this preferably goes to the primitive hexagonal phase. So we invoked this nucleation and growth process, and we calculated the activation, this energy barrier for crystallization to beta tin phase and crystallization to primitive hexagonal phase as a function of pressure. And what we have shown in this paper, that as you increase pressure, the required activation barrier actually reduces more rapidly for primitive hexagonal. So initially, though primitive hexagonal phase may not be that preferred, but in the pressure regime where the crystallization takes place, crystallization to primitive hexagonal phase becomes more favorable. And this is also evident in the nucleation rate plot. So nucleation to beta tin phase actually has more nucleation rate at relatively higher pressures. But before that, the nucleation to primitive hexagonal phase takes over. And that's how you have a crystallization in the primitive hexagonal phase. Okay. Now let us come to another phenomenological theory that is very famous, that is Landau theory of phase transitions. So Landau basically tried to formulate a general theory of continuous phase transitions, which were like second order phase transition as per the Unfest classification. And these phase transitions are basically described by the symmetry change. For example, magnetization. So Landau basically focused on this kind of phase transitions. So he tried to explain these phase transitions by expressing the free energy in terms of order parameters. Now, what is an order parameter? So order parameter is something that describes the instability of phase across phase transition. So it has 0 value above the temperature where there is initial phase, and it has some non-zero value below the temperature when there is a phase transition. So basically he focused on continuous phase transitions, which are more expressed by this plot, where the order parameter gradually increases from 0 to some value as you further go down in temperature. Now, of course, this free energy should have symmetry considerations of the system. So there should be the free energy, same free energy expression should describe both initial and final phases. So we have to take symmetry consideration in order to define this free energy. So he considered that if we consider a Taylor expansion of free energy as a function of order parameter. So G naught is free energy when there is a equilibrium, if this is an equilibrium state at higher temperatures or when the order parameter is 0. As soon as you cross this transition temperature, very close to the transition temperature, there will be some changes in the free energy. And this can be expressed by some higher order terms of this order parameter. Now, as I told, there will be some symmetry considerations. So we cannot have all these terms. For example, if we cannot have this odd terms, if the free energy is symmetric with respect to the order parameter. For example, if in the initial phase where T is higher than Tc, you have this kind of free energy curve. So the minima of this free energy is at order parameter equal to 0. So this has to be symmetric with respect to the order parameter. So in this case, we cannot have this odd terms because this odd term will lead to instability at this order parameter value, that is 0. So you will have some lower energy at some negative values of order parameter. So we cannot have these terms. So we can eliminate these terms. And then across the phase transition, the curve should modify such that we have some non-zero value of order parameter. And as I told, we want to explain this continuous phase transition where order parameter evolves from 0 to some finite value. So there should be a continuous change for the minimum free energy at some order parameter value different from 0. So for that, we have to tweak these coefficients. So now when you don't have these odd parameters, you can express free energy like this. And in order to have the stability at order parameter values other than 0, there should be some change in the coefficient which contributes to the square term. So as you know, this is depending on the square of the order parameter, this term is depending on the fourth power of the order parameter. So this function will vary more steeply at higher order parameter values. Whereas initially for some small values of order parameter, this function will vary more rapidly as compared to this value. So if we have the coefficient of this second order term, it changes the sign across the phase transition. So this will actually try to reduce the Gibbs energy at higher order parameter values. But then at higher order parameter values, this term will take over. So this is how your free energy curve will change. So you can see initially only order parameter 0 is the minimum energy configuration. And as you decrease temperature and you reach Tc, you have a very shallow potential well, which means that all these order parameters are accessible. So there will be large fluctuations at this T is equal to Tc. And then as soon as you go below Tc, you will have some value of order parameter very close to this 0, which will have the minima. And then at subsequent lower temperatures, this minima will shift to some different values of order parameter. So in this case, this describes the kind of phase transition like magnetic phase transitions. And you can clearly explain this phase transition by this formalism. You can clearly reproduce the evolution of magnetization. Here order parameter is magnetization. And it clearly describes the behavior of the order parameter as a function of T by T. So here one interesting point to note is that when you have expression for order parameter, which you can calculate by finding out the solution of this curve. So this will have three solutions. This is unstable solution and these are stable solution. So this stable solution corresponds to the order parameter values given by Tc minus T divided by some constant. This is below. If you see this expression has parabolic shape. So the order parameter is basically depending on the half power of this temperature. And this is one of the critical exponents. So you can very easily, by the formalism itself, get the value of the critical exponent. Of course, the critical exponent value 1 by 2 is under the mean field approximations. And in most of the cases where mean field approximation is valid, you will find that this critical parameter, which is also called beta, its value is 1 by 2. So you can easily get this critical exponent by this simple formalism. This is the power of this Landau theory of phase transitions. So researchers thought of using this formalism for describing other kind of phase transitions also, like first order phase transitions. How to do that? So for example, let us consider a case where its symmetry is such that you can have odd power of the order parameter. For example, you can have a phase transition where only positive values of order parameter is allowed. For example, order parameter is a scalar quantity. You have only positive values of order parameter is allowed. And the symmetry does not forbid you to take this third order term. In that case, you will have a free energy curve like this. Of course, here you have to put some restriction on the coefficient of this third order term, because you want to have this transition at some temperature below Tc. So there should be some minima appearing at some positive value of this order term. So the coefficient of this term has to be negative. Now let us see how this free energy curve evolves as we go on reducing the temperature. So initially, when the temperatures are very high, you will have certainly minima at the order parameter value equal to 0. But as soon as you reduce the temperature, you will see there is some flattening of this free energy curve close to some value of order parameter. And at certain temperature, we can mark it as T star, which is also called the spinodal temperature, first spinodal temperature, where you start getting some metastable phase. So you have a point of inflection, and then you have some region where the curvature is like this. This corresponds to the stable, metastable phase. And as you further reduce temperature, this metastable phase has lower energy, and it reaches to almost equal energy to that of the phase which corresponds to the zero value of order parameter. So this corresponds to the equilibrium between the parent and daughter, because the free energy is same. Of course, there is a barrier, so there will be some thermal fluctuations are required to cross this barrier. But then at Tc, these energies are equal. And if you further reduce the temperature, this becomes your stable phase. The daughter phase becomes your stable phase, and the initial phase becomes the metastable phase. And then there is a certain temperature which you call a second spinodal temperature, where this initial phase becomes unstable. So if you plot order parameter versus T by Tc plot, what you observe is that there will be a hysteresis. And this is clear-cut signature of first order phase transition. So if your symmetry permits, and you can have a cubic term, and where the order parameter is scalar, you can describe the first order phase transition by this formula. Okay, now come to the case where the order of transition is first order, but the symmetry does not allow the third order terms. In this case, Devonshire actually extended this Landau theory by adding some more term, higher order term, like n to the power 6, order parameter to the power 6, in order to explain this kind of phase transition. So the basic idea is you should get the order parameter value non-zero suddenly. Means across this transition, there should be discontinuous change in the value of order parameter. So the free energy curve should have a stable phase at some finite order parameter value. There should be discontinuous change in the order parameter value. So this can be explained, this kind of free energy can be described by this higher order expression. Of course, in this case, as we discussed earlier, there will be a different dependence. There is a different dependence on the order parameter. So at very small value of order parameter, this is dominant, but as you increase order parameter values, this becomes more dominant. At high order parameter values, this term becomes very much important, which this becomes very dominant. So if you can have positive contribution from this n square term, negative contribution from this term, and again positive contribution from this term, you can have this kind of curve, where order parameters can discontinuously change from 0 to some value, which corresponds to the minimum free energy. So there will be a phase transition, a first order phase transition with discontinuous change in the order parameter value. So this is a kind of formalism Devonshire used to explain ferroelectric phase transitions, where you cannot have the odd term, but still you can describe the first order phase transition by this, including higher order term. So here interesting point is this T is equal to Tc. So if you see this curve, you have three stable solutions. So this is also called tri-critical point. Okay, now we have talked about homogeneous transformation. So far we have not considered heterogeneous transformation, or where there are domains. What happens in case there are domains, which is practically the case in all real systems. So for this, another modification has come in the Landau theory, that is the Ginsburg-Landau theory. So in this case, you cannot describe the entire system by a single domain. There will be definitely several domains. There will be regions of the transformed and untransformed region. So the order parameter will be a function of distance. It will be a spatial, it depends on the position. And also there should be some gradient of the order parameter, which describes the changeover from one phase to another. So now in this case, we cannot define a Gibbs energy which is same for all the spatial positions. So what we have to do is, we have to integrate this Gibbs energy over entire space. And in this expression, different order parameter terms will also be the function of the position. Because in some region it may be in the ordered phase, or in some case it will be in disordered phase, means initial phase and final phase. So this has to be dependent on the position. And because there is a gradient of this order parameter, we have to include some gradient term also. But the order of this gradient term has to be such that it does not compromise the symmetry of the free energy. So this is the higher order term of this second order term of this gradient, which basically invariant under the spatial orientation. This we have to use in order to write the Gibbs free energy. This is called the Ginsburg-Landau function. So to describe the phase transitions where there are inhomogeneity, where there are domains, we have to invoke this free energy. So I will not go into detail of this Ginsburg-Landau function. So in fact, this is very useful formulation in order to describe the phase transition, like in superconductivity, and when in ferromagnets where you have domain balls. Probably this will be part of the talk will be given by Prayake Mishra, who will talk about high pressure, low temperature phase transitions, high pressure, high temperature phase transitions. So I will not go into detail of these formalisms. So far we have discussed this Landau theory in absence of external field. So in the next talk, I will talk about what happens when you apply external field, how the nature of this Gibbs energy curve changes as a function of external field, and how the nature of phase transformation changes. So this will be important to introduce what are the pressure-induced phase transitions, because pressure acts as a field in order to induce the phase transitions. And then I will also discuss about the mechanism of phase transitions under high pressures with symmetry considerations, and how they are evident from the vibrational modes like soft phone on mods. So all these things will be the topic of discussion in the next talk. So I will end the talk here, today's talk here. Now, now we can have questions. Unmute. So if there are any questions, you can post in the chat box at WebEx or YouTube. Maybe we can discuss live also, whoever are present. Okay, one question has come on YouTube. How to differentiate between morphotropic phase boundary and polymorphic phase boundaries? Okay. I would say that morphotropic phase boundaries that I discussed, this is basically based on the compositional change. So when you change, like in solid solution in PZT, when you change the concentration of lead titanate and you go across a phase transition from bromhydride to tetrahydral phase, this I should describe. This is the morphotropic phase boundary. Whereas in case of polymorphic phase boundary, I would say that the system chemical composition of system is same, but you have different polymorph. You have different stability region in the thermodynamic state. So that I should call polymorphic phase transition. Is there any question or comment? Another question has come, what is the key parameter which decides the type of phase transition which will occur in the system? Okay, so basically here I will be focusing more on the thermodynamic phase transitions, basically pressure induced phase transitions. So I will be more concerned about the transition where pressure is the key parameter. Of course, in different thermodynamic conditions, different thermodynamic parameter can be a key parameter for the phase transition. For example, if you have fixed pressure and you want to change the temperature, so temperature can decide the phase transition. So I think it should be it should be the process dependent, thermodynamic process dependent. Or for example, if you yeah, it should be basically thermodynamic process dependent, I would say. The field actually influences the free energy. So this may change the nature of phase transition. Also, it can change the thermodynamical parameter value at which phase transition should happen. So it's a combination basically. So in the next talk, when I will talk about the effect of field on the free energy, then I think this should become more clear. What parameter plays important role as there is a phase transition? Yeah, I think with no more questions, we can end this session today. And we will see in the next talk on Friday, that will be more focused on the high pressure phase transitions, particularly considering the symmetry point of view. Thank you.
Thank you, sir.